loi, mais moi je suis contre. La préférence, c'est de
Ok, bonjour, bonjour, bonjour à toutes et bonjour à tous. Ça me fait plaisir d'accueillir Laurent Duchemin, que je connais depuis longtemps, hein, qui a fait il y a très longtemps une partie de sa thèse au LMM, à Scott, à la grande époque de Scott, lors du désamiantage. Excusez-moi, c'est les vieux qui racontent leur vie. Et puis après, il a fait plein de post-doc dans des équivalents anglais d'Alembert, hein, à Londres et à Cambridge. Et puis il a été maître de conf à l'IRFE à Marseille. Et plus récemment, il est chez nos voisins et amis et collègues du PMH, ici même bien à côté. Et tu vas nous parler de, de contact de gouttes avec une surface et de plein de choses, de plein de belles choses sur les interfaces. Ah oui, un truc important pour les petits jeunes, c'est que je crois que Laurent, il essaye de résoudre des équations un peu simplifiées et que c'est un sacré travail en fait de résoudre ces équations qui, bien qu'elles sont simplifiées, sont difficiles à résoudre.
Je vais essayer de montrer ça. Ouais.
Ouais, je pense que c'est ça qu'il va essayer de nous montrer. Je pense que c'est un message aussi important d'un point de vue numérique. Bon, à toi Laurent.
Merci pour l'invitation. So I'm going to switch to English. Uh, so I'm going to talk about a problem I've been interested in for a long time through two main problems. So here you can see a numerical computation of the impact of a drop on a solid surface, and there is a gas between the drop and the surface such that it's not going to contact, and you can see that there is a small gas dimple entrapped between the drop and the solid. So before talking about these two subjects, so this one is one of the two, I'm going to talk briefly about work in progress in my lab. So I have two PhD students working on similar problems. So the first one is Hugo Del Rio working on an experimental case of Leidenfrost, cold Leidenfrost effect. So you take a drop of Perrier and you put it on a super hydrophobic surface. And because the concentration of CO2 is large inside the drop and zero outside, it's going to escape from the drop, and then the drop is going to levitate. And so Hugo is studying this effect by using interference fringes, seeing the drop and the gas layer from below. And here, what you can see, so this is a profile that you can find by studying the distance between the two successive fringes. And what happens is that because the concentration is CO2 is going to decrease in time, then the drop is going to settle and finally touch the solid. So this is the main problem he studies. This is mainly experimental. And the other one is Gareth Kergoulet, who's working on a numerical analog of Leidenfrost effect, but for a drop on a thin liquid film. So if you do that, if you suppose that there is a temperature difference between the drop and the film high enough such that there is going to be evaporation at the surface of the drop or the liquid film, then it's going to levitate on the thin film. So he solved this numerically with a homemade code. I will talk more about that later on. And so here, if you fix at a given, so these are dimensionless numbers, and this one is related to the temperature difference. It's linear in the temperature difference between the drop and the film. Then it's going to, because of shear, it's going to push the liquid film away from the zone of the droplet, and then it's going to dry the liquid film below. So one of the main questions is whether or not it's going to dry the solid surface, and is there a bifurcation point for which, or a delta T for which it dries and below which it doesn't dry the solid surface, the liquid film, sorry. And so if I change the delta T, then here what he obtains. So it's of course, so if delta T is higher, then the distance, the mean distance between the drop and the liquid film is going to be larger. Okay, so I will talk about the equations later on. Okay, so the first problem, sorry. Okay. So I've been working on these two subjects with Christophe Josserand. So he was in LADIX, and a lot of you know him, I guess. And so the whole story started with this amazing paper from Sid Nagel's group in 2005. I think this is the reason why there are 20 sessions at APS about drop impact, and why half of D'Alembert is working on this. So it's a very simple experiment. So he managed to film with a high-speed camera the impact of a drop on a very smooth surface, and he decreased the ambient pressure from the atmospheric pressure to 0.2 or times the atmospheric pressure. And when the gas pressure is low, then the corolla doesn't develop, and it's like it's extremely flat. So people have been trying to understand this. I don't claim that I'm going to explain you why it does this, because I don't think that anybody understands that. But I'm going to give some numerical clues about why we observe this behavior. So this was really stolen from Sid Nagel's website. I couldn't find the video, so I grabbed the video from his website without copyright. So this is the drop impact at atmospheric pressure. So you see the rise of the corolla, and it's and the formation of small droplets. And if you decrease the ambient pressure, so this corresponds to the pictures I showed before, then the behavior is completely different. And so people started to wonder whether the gas film between the drop and the solid had some importance about the rise of the liquid corolla. So this is what I tried to study by writing a code. So if you so you can, so without using Basilisk, so this is a homemade code, you can suppose that viscosity can be neglected inside the drop because the Reynolds number is very large. So there are two dimensionless numbers that are relevant in this problem. The Weber number that compares surface tension to inertia to surface tension effects, and a Stokes number, which is the inverse of somehow Reynolds number, which is the viscosity of the air divided by the density of the drop times the velocity times typical radius. So if you neglect the viscosity effects inside the drop, you have to solve Laplace equation for the velocity potential and Bernoulli equation on the surface of the drop. So this is the main difficult task to do in this kind of codes, because it's 3D, so you have to solve Laplacian of phi equals 0 knowing the boundary conditions. And to couple the drop impact with the gas layer, we write a lubrication equation that relates the local vertical velocity of the interface to the pressure inside the gas film. So we can solve this numerically. It's quite complicated because it's very nonlinear. The main equation is linear, but the boundary conditions are nonlinear. And if you manage to write such a code, here is what you obtain. So after the dimple formation, so there is a scaling which is interesting, which is what's the thickness and what's the radius of this entrapped gas bubble. And then after that, you see the emergence of the very thin liquid corolla. And if you zoom on the contact region, so there is no contact, but if you zoom on the minimum film thickness region, then you can have a look at the resolution, which is quite high. So I used a boundary integral method to solve this problem, and the main advantage of that is that you can refine, you can put a lot of points in regions where the curvature is high or where you need a good resolution. Okay, so as I said, one first interesting point is the scaling of the entrapped gas bubble. So to find the scaling, you have to have a look at the equations. And so we suppose that the typical, so we want to determine the typical height of the gas entrapped bubble and the typical radius, L. So this scaling is just the scaling of a sphere approaching a solid. So this is the radial characteristic length when a sphere approaches at a distance h flat surface. Okay, and if you put, so this is a bit misleading because this is not the scaling for, this is a typical horizontal scale. This is not the, at this point, this is not the scale of the bubble. So if you put this into the lubrication equation and suppose that the deceleration of the interface is due to the radial pressure gradient, then you find a link between the deceleration and this pressure. And if you put these scalings into the lubrication equation, then you find a new equation that relates the viscous effects and this gas pressure. And this is a closed system for L and H. And you find that H goes like the Stokes number to the power 2/3, and L like Stokes number to the power 1/3. And I recall the expression of Stokes number here. So of course, it's quite easy to check that this is true. So by varying on a lot of decades the Stokes number, then we find that the height, so I did the same for the radius, but it works. So this is so we have a scaling with the numerical prefactor of the entrapped bubble between the drop and the solid. But of course, everybody knows the lubrication paradox, which says that if locally the interface is flat, then if you compute the pressure from lubrication equation, you find that for a locally flat interface, the pressure is a parabola in R, and it goes to infinity when h goes to 0. So it's impossible to touch, or this is the paradox. If you don't have a small scale structures on the surface, if it's smooth at an atomic scale, then it's not going to touch the surface. Okay, so what can we understand what happens if we neglect the surface tension effect? So if we take the case of an infinite Weber number, so the inertia is much larger than surface tension, can we predict what's going to happen? It's going to touch on a point, because I just said that it's not possible to touch when the surface is smooth. So can we find scaling for this? So the answer is yes. So I'm going to suppose that the horizontal scale is delta L. So this is the horizontal scale of the region that is going to touch the solid. And delta H is the typical vertical scale. And I'm also going to suppose that dH by dt is much lower than the advection of the interface. So this is a bit subtle, but it's like the advection of an interface. So dH dt can be smaller than this term, which is a convective term. I call delta P the pressure scale. And if we put these scalings and this hypothesis into the lubrication equation, we find a scaling for the pressure. And what can be seen from this equation is that delta P can go to infinity if delta L is much larger than delta H squared. Or it can be finite if the two are of the same order. And another question is what about the curvature in this limit case? So what we observe numerically is this series of profiles. So I took an infinite Weber number, so surface tension is neglected, and a small Stokes number. And then if you follow the minimum of film thickness, then it's going to touch indeed the solid surface on a circle. So it's not going to touch on the surface because it's impossible, but on a circle, on a point here. And I will show the curves just afterwards. If we plot the pressure, the maximum pressure as a function of the minimum height and the curvature, we have these two behaviors. So T goes from the right to the left, so because H naught decreases in time. And what we see is that the pressure increased like H naught to the minus 1/2, and the curvature, the local curvature of the interface, goes like H naught to the minus 2. So the idea, so I'm sorry, it may be a bit technical, but the question is whether we can understand these two scalings, and I'm not sure they are too obvious. So if we do the hypothesis that we can use a self-similar ansatz, saying that we rescale R and Z by their typical horizontal and vertical, the same length locally. And so we suppose that we have a self-similar ansatz in the region where it's going to touch the solid. Then if we put this ansatz into the equations, we obtain the following equations, which are which look a bit complex. And so all the time functions are in red in these equations, and the system is not closed if we don't do any hypothesis. But what we can see is that in this equation, which is the kinematic boundary condition, there is this term here that can be either small compared to 1 or large compared to 1. And this is going to give me two cases. And if I drop this term or keep this term in front of this one, then the system is closed and I can find two different singularity regimes. Okay. So here I reported the same system of equations. So what I call regime 1 is the case where H naught is much smaller than L. So the thickness is much smaller than the radial extension of the contact zone. Then this term can drop. And the system of equations for phi naught, L, R naught, etc., H naught is closed. And we find the following scalings. So the pressure goes like H naught to the minus 1/2, and the curvature like H naught to the minus 2, which is consistent with what we saw numerically. Yes?
I don't understand why it closes the system.
Because the number of unknowns is equal to the number of equations. No, but I dropped this term. And here you've got a function of time times a function of space equal a function of time times a function of space. So if you want these two functions to be equal, you have to have the prefactor to be equal to one another. And so if instead of dropping this term, if you keep only this term and drop this one, then you find another system of equations, and it's going to give you the following result, that the pressure is constant, which is not what we observe numerically, and that the curvature blows up like H naught to the minus 3. So I don't say that it's a definitive answer about this scaling, but at least we have an explanation. We know in the equations which term we have to neglect, and that corresponds to what we observe numerically. And so indeed, so we can predict, we can somehow understand that why the curvature blows like H naught to the minus 2 and the pressure like H naught to the minus 1/2. The surprising fact is that for this regime, if we write the scaling for L, the radial extension, then it is much smaller, much larger than the thickness, which means that the thickness of the film is larger than this Stokes number to the 4/3, which corresponds to thick films. So if we could go further in time towards the contact, and maybe we could observe the second regime. So we couldn't, numerically it's too difficult to go to this limit. So we were only able to observe the first regime. Okay, so now what happens when we take a finite Weber number? So in this case, as I said, it's not going to touch the solid surface, and instead we are going to see the emergence of liquid sheet, which thickness depends on the value of the Weber number, which is the ratio of inertial effects to surface tension effects. So if you take a large Weber number, then the sheet is going to be very thin, and if you have a small Weber number, then it's going to be very thick. So this corresponds to small velocities, if you want. And here I changed the the Stokes number. I took a value of the Stokes number in the gas film smaller than in the other computation. So to try to address the initial question about the corolla, it's interesting to have a look at the typical thickness of the film here. So the skating height, if you want, of the drop. So if I plot the minimum film thickness as a function of time, you see that there is a plateau that depends on the Stokes number, the viscosity in the gas. And the higher the Stokes number, the higher is the thickness of the film, which looks quite logical. And if we increase the Weber number, we also have a small effect, but which is much smaller than the effect of the Stokes number. The problem is that it doesn't address the initial question, because if you decrease the pressure in the air, you don't change a lot the dynamic viscosity. So the variation of a Stokes number does not relate to the decrease in ambient pressure. However, we can try to understand using the scalings for the singularity to understand the skating height. So we come back to the two regimes, and then we suppose that the capillary pressure is balanced by the pressure. And if we do that, we find two behaviors for the skating height that correspond to regime 1 and regime 2. And one is Weber to the minus 2/3, and the other one is Weber to the minus 1/3. And with what we observe numerically, so here I plotted the thickness divided by Stokes number as a function of the Weber number. And the regime that works is this one, so Weber minus 1/3, which corresponds to the second regime. So it's a bit puzzling. We don't have all the answers about this problem, but we somehow understand the behavior of this skating height as a function of the Weber number and the Stokes number. So we wrote a paper on this subject, and another one, because if we have a look at the typical gas film thickness, they correspond to a few angstroms, which is much below the mean free path, which is 70 nanometers. So at this scale, it's natural to take into account rarefied gas effects, and you can do that by adding a slip length on the. I'm not a specialist of that, but you can you can add a slip length on the solid surface, and it does change the scalings. And it introduces a new dimensions number, which is the ambient pressure divided by the kinetic energy.
What is the mean?
It's the typical distance between molecules, and it's at ambient pressure it's about 70 nanometers. So basically, the film thickness is much smaller than the typical distance between two gas molecules, which is so continuum mechanics doesn't work anymore. And so the other number which is introduced is the Knudsen number, which takes into account this rarefied gas effect. So I'm going to switch to another problem, which is completely different. It looks a bit the same, but it's very different, because in the first case, the ingredients were drop inertia and lubrication. And here, what you're going to see is a very nice experiment from this PRX. And on the left, you are going to see a drop which is deposited on a liquid film very gently, very slowly. And on the right, so on the left, the experiment has not been prepared very carefully. So there is a small, very, very small angle. And on the right, they've been waiting for a long time, such that the liquid film is extremely horizontal. And here you're going to see the difference between the two. So I said inclined, but it's so the drop is going to coalesce very quickly in 100 milliseconds with the liquid bath, with the liquid film. And on the right, so we can wait for quite a long time because it's going to take more than a second. So it's a bit puzzling. It looks, it's quite, just with these videos, it's quite difficult to understand what happens. So what they did in this PRX is that they had a look at the gas film with interference fringes. And so there is a very, very thin film between the drop and the liquid film, and it's going to drain because of the weight of the drop. So the air is going to be pushed away from the contact zone. And so, of course, it takes some time. And after a second, then we are going to reach a thickness at which van der Waals forces can be important, and then it's going to collapse. So the main question we wanted to address is what's the drainage rules of this very thin film. And it's not related to the dimple I was talking previously, because there is no inertia in this problem. So the equations are different. So here is how we modeled this problem. So we have a thin liquid film, a thin gas film, and a drop. So what we did is that we wrote lubrication equations in the liquid film, in the gas film, and simply hydrostatic pressure in the drop. So we neglect the motion inside the drop, which is somehow a strong hypothesis, but this is the hypothesis what we make. No, we take into account capillarity. And yeah. So I just want to show you the equations. So it looks simple, but it's not that simple. I will explain on the next slide why it's very difficult to solve. So we have two partial differential equations, one for the liquid film thickness and one for the gas film thickness, or the H2 if you want, the interface between the drop and the air. And we have boundary conditions which take into account surface tension and the continuity of velocities and shear stress. Okay, so it can be written. And to show you, as Pierre-Yves asked, why it is so difficult to solve this equation. So if you develop the terms, here is what you obtain. So it could be simple. It's just a large number of terms, but the difficulty comes from the fact that there are high-order derivatives. So for instance, here you've got a fourth-order derivative in space. And if you use a naive explicit time stepping, if you want to solve that, then you're going to have a constraint in delta t, which is delta x, delta r to the power 4, which means that if you multiply the number of points by 10, you have to divide the time step by 10 to the 4, which is impossible. So what we do with that is that we write semi-implicit codes, meaning that we take all these terms with the higher order derivatives, and we treat them implicitly, which adds some complexity to the code, because you have to invert a linear system at each time step. And so I won't give you more details, but just to say that it's quite tough method. Is the yes. Yes, but it's finite. It goes to 0, but it's always finite. H, capital H is the distance, is the gas film thickness. Okay, so in the end, you can write a code that does that, and this is what Garrett is working with. And here are the dimensionless numbers that are relevant for this problem. So there is the bond number, which relates the gravity to surface tension, which is related to the size of the drop. So if it's order 1, then the capillary length is equal to the radius of the drop. So there are also two Stokes numbers, which are defined like this, based on the freefall velocity square root of gr. This is a choice, but we can make other choices. And there is another dimensionless number, which is the thickness of the liquid film with respect to the radius of the drop. So here, so if you solve these equations, here is what you're going to obtain for a Stokes number going to infinity, which means that we consider the liquid film to be solid. Okay. So if you do that, you're going to obtain this. So the scale in x and y is not the same, so it's much thinner than that. And the red curve is the pressure in the gas. Okay. So if you do that, here is what you obtain. So it's been studied a long time ago, but what you obtain is a dimple, okay, which is going to drain in this very, very thin region. So it is very difficult to evacuate the gas because it's extremely thin. And the pressure has this simple behavior. It's a plateau in the dimple region. So it's a constant pressure that is exactly against the weight of the drop. And it drops from this plateau value to 0 in this very small region. So we can do scalings for this pressure and the dimple. So it was known before. You can find JFM papers from the 60s explaining this. So this is somehow an asymptotic matching. So I'm going to, I'll come back to this later. I'm going to match the curvature of this region to the outer curvature of the drop. And I'm going to match the slope in this region to the slope of the dimple, which is a parabola. So this is basically what we do when we do asymptotic matchings. So this is the matching the curvature of the thin region with the outer curvature. So this, I suppose here that the drop is large, such that the curvature of the equator of the drop is 1 over the capillary length. And here is so I use lubrication equation, and I can relate the thinning of the dimple with the minimum height, the Bond number, Stokes number, etc. And the final scaling is what I said just before, is a matching of the slope with the slope of the parabola underneath the drop. So if you do that, you have, again, the system is closed, so you can find the scalings for h bar, which is the mean height, and h min, which is the minimum height. And so it was known before, so we find that the mean height goes like t to the minus 1/4. So we have a scaling in time for the decrease of this height. And the minimum height goes like t to the minus 1/2. And it works perfectly. So this is quite simple and well known. So the question is what happens when we replace the solid surface with a liquid film? So if we do that, so this is the same movie, but with a finite and small Stokes number inside the liquid film. So here is what we get. So the liquid film deforms because it's sheared by the gas outflow. And the pressure is not a plateau anymore, but it evolves on a scale which is slightly different. But the main difference between the two computations is that the gas film is much thinner. So can we understand this with scaling? So this is the final profiles. So here on a solid surface and here on a liquid surface, and you see that the gas film here is, which is entrapped, is extremely thin compared to the left. So there is something different in the scalings that I'm going to explain now. So sorry. So if you compare, so this is capital H, so the thickness of the gas film as a function of time for the solid case and the liquid case. And indeed, you see that at the end, so the criterion for to stop the simulation is the same. And what we see is that at the end, the gas film is, I would say, 10 times smaller than in the solid surface case. So we can redo the same scalings, try to redo the same scalings. So we match the curvature of the thin region to the outer curvature. We use the lubrication equation and write that and use the scalings into the lubrication equation in the gas film. The problem comes from this equation because we cannot match anymore the slope to the inner slope, because what we observe numerically, we don't have any clue for this, but what we observe is that the minimum height scales like the mean height. So if we make this hypothesis, which we couldn't really explain, this is just a numerical observation, then we find scalings that are completely different than before. We find t to the minus 2/3 for the two typical thickness, which means, so it's a bit more interesting than it looks, because the minimum thickness is going to be, if we have a threshold for the minimum thickness below which van der Waals forces are important, then this typical thickness is going to be reached much before in the solid than in the solid case, which means that it's going to make contact with the liquid much before the case where the surface would be solid. Yes.
But it doesn't appear in this new scaling equation. Sure. Because you could do Stokes to infinity to get the former scaling.
Yes, you're right. I think it's in beta. You're right. Yeah, I think it's inside constant beta. So we have a completely different behavior in terms of time to reach a given threshold for the thickness. And if we make a parametric study by varying the Stokes number, so the viscosity of the liquid film, then, here is the time it takes for a given Stokes number to reach a given thickness, then the surprising fact is that we have a maximum. So there is a maximum in this curve, which is a bit surprising, and we couldn't have any answer for this. So if we take, for instance, 4 × 10⁻⁴, which is a dimensionless quantity, but it's a small typical thickness of the film, then we are going to reach a maximum here. So which means that which does not correspond to a solid surface. It's a finite Stokes number, but it's very large. So there are still open questions about this problem. So I'm going to talk about open questions that I'm interested in now. But so before that, to conclude on these two problems, so it seems that the dimple occurrence is quite universal, even if the origin of the dimple can be very different from inertia to gravity drainage. The dimple deflection on a solid is much different from the dimple deflection on a liquid film. So there is a faster dynamics in this liquid case. So the question for people who do experiments is that whether we can measure this speed up. I think it's an interesting question. And we can take the liquid film as thin as we want. So in the perspectives, I would say that it would be interesting to do a parametric study by varying the bond number, so the volume of the drop, and maybe think about forces or geometries to speed up the coalescence. So what about open questions? So I've been interested for quite a long time now about so the ambient pressure. It is still an open question, I think. And what about the Leidenfrost effect? So if you put delta T between the drop and the substrate, which can be liquid or solid, then if the temperature difference is high enough, then the drop liquid is going to evaporate, and the gas phase is going to be between the drop and the substrate, and then the drop is going to levitate. And the condition we have to write for this velocity of the gas, of the vapor phase, is the Stefan condition, which relates the heat flux at the interface and the latent heat of vaporization. Okay, so you can write this model. And then this is included into the lubrication equation as a source term. So it's not going to drain until contact, but it's going to remain like that because of this source term. Okay. So what's the main, in my opinion, what's the main question about this phenomenon? I think it's been known from the 60s that this is a metastable, which means that if you put a drop on a hot substrate, on a hot solid surface, and you measure the evaporation time, then if you are above the 100 degrees, if it's water, then it's going to you're going to have a value. And then if you increase the temperature and you redo the experiment, it's going to take less time to evaporate, and it's going to decrease again. At some point, so this is the 66 graph, but it's been rediscovered since. Then at some point, which is not known, we don't understand the value of this temperature. At some point, it's going to go. The evaporation time is going to be increased by a large factor. And the reason is that because the drop levitates above the solid surface. Okay? And if you do the contrary, if you start from the right from high temperature differences and decrease the temperature differences, then you are going to stay on this branch. Okay, so there is a hysteresis which is not understood. So there are recent experiments about this. So this is not a drop, it's a solid sphere, which hot, which is put at the surface of a liquid. And D is the thickness of the gas film between the liquid and the solid. And so the red points corresponds to the temperature going from 100 degrees to higher temperatures, and the blue ones to the case where we decrease the temperature. So there is clearly a hysteresis, and what is not understood, and so a lot of people have been thinking about that from a long time, and the question is what sets this temperature? Why is it here 250, and why is it not 102 degrees? Or so this is not understood. But people have tried to find clues about metastable instability, and recently there was this paper by Pierre Chantelot and Detlef Loser, PRL, and they explain, so I'm not going to explain much detail about this, but they explain the hysteresis by seeing in the experiments using interference fringes that there is a percolation phase transition, which means that if it touches at one point, then the location of the touchdown of the drop is going to be related to a percolation process. In my opinion, it doesn't explain why it is subcritical, but at least it's a clue to prove that it is indeed subcritical. And there is also, so these are a list. This is a list of ideas I think are interested to explore. So this is another paper by Ambre Bouillant about the self-excitation of Leidenfrost drops. So when they are in a Leidenfrost state, so there is this finite thickness gas film, then they spontaneously oscillate, and the oscillation is related between the coupling between the gas phase expansion and capillary waves. So they measured this, and they showed that there is a resonance between the lubrication layer and the emergence of capillary waves. But the puzzling, in my opinion, the puzzling issue is that these oscillations appear with a solid. So you can do a much simpler experiment. You take dry ice, which is at minus, I don't remember the temperature, but maybe minus 80 degrees, and you put this on a solid surface at ambient temperature. And what you are going to observe is a spontaneous oscillations, vertical oscillations of the solid dry ice. And this is not understood either. So this is, I think this is a truly open question, because if you write the lubrication equation, which is probably extremely relevant in the very thin gas layer, then whatever you do, it's going to, every instability is going to be damped by viscous effects. So there is no mechanism to amplify the oscillations. So if you do, you can do a very simple numerical code. You take a plate and you write lubrication equations underneath with a Leidenfrost effect. And then whatever the initial condition, the weight of the plate, whatever the setup you choose, every oscillation is going to be damped in a finite time. So there is no mechanism to amplify the vertical oscillations. So to conclude, I've tried to make a list of what could be interesting to study to understand these subcritical bifurcations. So there may be 3D effects, because I've been talking only about axisymmetric simulations and 2D simulations. Maybe there could be 3D effects, like a coin on a table. It could be there could be an oscillation related to a variation in theta. Rarefied gas effects could have an importance as well. Compressibility, I've been trying to take into account compressibility. The Mach number is very small, but the gas is confined into a very thin layer, so it could be that compressibility could be important. There may be some Marangoni effects between the bottom and the top of the drop, but the oscillations appear with a solid, so in this case, we cannot explain the oscillations with Marangoni effects, maybe into the Stefan's condition. And finally, there is one interesting, I think, remark about the value of the Reynolds number, because we always want to suppose that it is either very small or very large, but in this case, it's of order 1. So the solution of Navier-Stokes equations with a Reynolds equal 1 is something I could investigate with Basilisk, probably. And to conclude, my advice is to read this great review paper from James Prittles that talks about mainly these subjects, the contact between a drop and a surface, including the Leidenfrost effects. And on this, I conclude. Thank you.
Okay, merci beaucoup. So thank you very much. Question.
Thank you, Laurent, for this presentation. I was intrigued by the angstrom length that you mentioned at the end of your first problem. I was wondering how physical it is to have a gap thickness of a few angstrom, because you mentioned later the influence of van der Waals forces.
Yes.
And I was curious if there is like any experimental demonstration of that, because with interferometry, you cannot go as small as angstrom to measure it. So yeah, I was curious.
Yes, I agree. So I can't really answer this question, but the fact is that we used continuum mechanics, and the point is that I just say that it doesn't work at this case. About the papers that use interferometry I'm not sure there are papers about the drop impact that measure truly the thickness, the local thickness. I'm not sure about that. This is basically this is a numerical result. I mean, the fact that it can reach a few angstroms. There is no experimental evidence about that.
And do you believe it could be like that in reality?
Well, no. I believe that van der Waals forces are going to be important before this. Yes, sure.
For the presentation, and I was wondering, at first you showed us a figure with different atmospheric pressures which affected the droplet movement. And in your simulation, did you test with different atmospheric pressures that at the end?
No, because it's incompressible, and so I cannot change the ambient pressure. This is zero, if you want.
So then you are saying that the compressibility definitely plays a role on the on that effect of the coordination.
Yes, or these rarefied gas corrections.
Okay.
Yes, I don't claim that I have the answer about what's the effect of reducing the ambient pressure, but in my incompressible simulations, I cannot test this idea. Because,
Thanks a lot for the presentation. I have a question about the dry ice oscillations. Do you think it could be because of inhomogeneities on the surface of the dry ice, and then you have kind of a sublimation rate that is different throughout the...
Well, I tested a lot of ideas. If you have
Okay.
any idea, I'm really interested in that, because it's really, for me, it's really puzzling. Ambre did very, very extremely careful experiments about this. And what I can say is that so it's measured by the weight of there is a force measurement with which is very precise. And I think that during the sublimation process, the surface of the dry ice is going to be smoothed. So it's initially there may be some inhomogeneities, but I don't think it explains why it's going to oscillate, because after sometimes it's extremely smooth. And I thought at one point it could be a motion like that instead of a vertical motion, but I don't have any clue, and there is no amplification mechanism for these oscillations.
If you redo the simulation with a plate and add the homogeneities at the beginning, what does it do? Does it actually smooth out, or do you have stuff that is different?
You talk about the simulations, or?
Yeah.
Yes, I didn't try that, but
okay. Thank you.
Thank you for your presentation. For this, I have also a question for this simulation, this experiment. Can it relate to the paper of Josserand, Rodolphe, Rivet? You remember when they were doing a droplet impact on a super hydrophobic surface, and then they compare it to droplet impact on ice, a very cold surface, and then they show that they behave like super hydrophobic. And it's kind of, yeah, for me, there is a similarity between
yes.
the phenomenon observed when you have oscillations. And so that's an idea that I was thinking about.
But in their case, I think they have contact between the drop and the...
Yeah, at some point they have contact. Okay. Yeah.
In this case, it's really, there is absolutely no contact.
Yeah.
It's,
Maybe. Thank you.
Just on the precision on this graph, the frequency is the same all over the experiment, although the
yes.
ice is sublimating.
Yes.
Okay.
And there is one harmonic frequency, which is twice, I think, the main frequency we observe. Wait.
No, but my question was that okay,
the peak,
there are two frequencies, but
remains
it's
the same.
Not it's not frequencies that shift over time because the mass increases.
No, this one is purely numerical. It's about numerical point of view. Why your interface oscillate slightly like this? When you show the first video, the
no,
first
it's
movie,
because
there's slight oscillations
issues, I think. Yes.
Yeah, it was just.
Yes.
No, is it numerical oscillation or just the visualization?
Maybe just the visualization. I'm quite confident about my simulations.
Ok, bah, ce sera le mot de la fin. Alors super, mais encore merci Laurent.
Merci.